Greetings. We'll work an example to show how this discounting formula process works for the example of wood chip bioreactors. To do this process, the basic steps are you itemize all of the costs that occur over the life of the practice or over the planning horizon that you're thinking. So for a cover crop is an annual practice, but you might be thinking to do a cover crop for 10 years. So you would itemize the cost of that cover crop over all 10 years. Itemize all the costs that occur. Step 2 is to identify when those costs occur within the planning horizon that you're thinking about. Step 3 is to bring all of those costs back to present value using discounting formula. And then step 4 is to amortize those costs to get an equal annual cost over the life of that practice or over the planning horizon you're thinking about. So I wanted to do an example with bioreactors just to run through how this process is done. I've already listed some itemized costs here. There's costs that occur in the first year when you install the bioreactor initially, and then there's costs that occur over time, over the planning horizon that you're thinking about. Now, not all these, I'm not listing all the costs. This isn't an exhaustive list of all of the costs for bioreactor installation and maintenance, but this is just an example to give you an idea of what this process looks like again. So one of the first things I'll do is decide my planning horizon. I'm interested to think about the costs involved in bioreactors over a 20-year period. I also need to know my discount factor up front. So my discount rate, we talked about in the lesson, for 2019, for water resources projects, my discount rate is 2.875%. So I can plug that into my spreadsheet early on, 0.02875, because I want this as a decimal, not as a percent. I'll calculate my capital recovery factor in a minute. Let's go to itemizing our costs. Up front, the installation costs up front for a bioreactor include wood chips, control structures, miscellaneous tile and fittings, plastic liner, and then drainage contractor labor. So for wood chips, I happen to know some of these costs. I'm going to say I have a bioreactor that needs 150 cubic yards of wood chips. I know an average cost for wood chips is about $25 a cubic yard. So you just go through the process of itemizing and then putting numbers to each cost associated. To control structures, one will cost me about $1,000. The second larger one would be about $1,500. Miscellaneous tile, I'm just going to estimate in here $500. Plastic liner, again, I'm familiar with these costs, but you would want to look these up with either quotes that you get from vendors or costs that you find on the internet. Now my drainage contractor labor, that one is a little bit harder for these initial costs, these upfront costs, because it's a labor cost. And so this is where our custom rate surveys come in, drainage contractor labor. For drainage contractor labor, I'm going to go to the custom rate survey and look at the backhoeing. It's an hourly cost, and it looks like the average charge across the 18 survey responses they had in Iowa recently was about $96 an hour for backhoeing. The median is a little bit lower, but I'm going to be conservative and use $96 an hour. Or I could use $100. Let's use $100 an hour because I see the range goes from 65 to 135. Let's use $100 an hour for backhoeing. I still have to know how many hours. Well, I'm going to guess or estimate it takes 2 guys about 2 days to build a bioreactor. So a drainage contractor and his assistant. So I'm going to say equals 2 guys, 2 people, I should say, times 2 days, times 8 hours a day, times $100 per hour. So that gives me a total cost for my drainage contractor labor for the initial installation of $3,200. So let's stick up at the top of the table with the capital costs and keep filling this table out. When does the cost occur? Well, it occurs in actually year 0 for this process. So I'm filling in zeros here because all of those are year 0 costs. Those are upfront costs. The formula is that there isn't one because it's already in present value. Okay, so that's really easy. This is the easy part of the table. All these costs are already in present value because they're happening today when I install the bioreactor. So in my total present value column, I'm just going to set all those costs equal to the cost that I calculated. Now, moving to the next part of the table. the first recurring cost is time to manage the bioreactor every year. And this is pretty minimal. You're going to mow it a couple times a year. You're going to go out and change the control structures. There's very minimal maintenance, but we still want to account for this. So this is a labor cost. I'm going to go back to my custom rate survey. I'm going to look at, for mowing, let's just use that as a price. Mowing fence rows or ditches, that would probably be comparable. So I'm looking at about $75 an hour. I'm going to try to be a little conservative, $75 an hour for mowing or general maintenance. So I'm going to do equals, it takes one person, being very generous, maybe 3 days a year times 8 hours a day times my $75 per hour based on the custom rate survey. So my annual maintenance for my farmer is $1,800 a year if I'm valuing his time. Next, I know that I want to replace the bioreactor in year 10. So thinking about my planning horizon of 20 years, that's what I'm trying to account for costs over the whole 20 years. I'm going to have to replace the bioreactor wood chips in year 10. So I need to account for that cost. Wood chip replacement. And I'm just going to assume those costs of replacing the wood chips is the same as the initial cost of buying the wood chips. Contractor labor for wood chip replacement, I'm just going to set that to the same contractor charge I had before. So same thing, and then replace the control structures in year 10. I'm going to set that to the same cost too as the initial cost of those control structures. Now let's think about when these costs occur. Time to manage the bioreactor happens in every year. So this is basically year 0 to N, which is my planning horizon. So basically the first year all the way through year 20 for that one. Wood chip replacement occurs in year 10. I wrote that out in the table. Okay, so now is the slightly more complicated part. We just have to make sure we're going to use the right discounting formula. So let's start with this first one, time to manage the bioreactor each year. Is that a single sum or a series? It's a series. So is it a terminating or perpetual series? Well, it doesn't go on forever because we have a planning horizon of 20 years. It does happen every year, but I would say terminating series, is it annual or periodic? It's annual because it happens every year. So I would say terminating annual series. So here is where we type in the formula. I have my formula written here on the screen, so equals A in this case is my cost, my itemized cost, times, I'm going to throw in a couple parentheses here, times 1 plus I, my I is here, raised to the power of my N is here, in parentheses, minus 1, in parentheses for the top, divided by, start parentheses for the bottom, I times parentheses. I tend to be liberal with my parentheses because having extra doesn't hurt, but not having enough does hurt. So 1 plus I raised to the N. N is my planning horizon. Okay, so I in parentheses for that. I in parentheses, add in a second parentheses to end for the bottom, for the denominator, and then I end for the entire inside part of that formula. Okay, let's see if we got that right. Okay, so notice this. The farmer is spending basically $1,800 in his time every year to manage the bioreactor. However, when you look at that $1,800 every year for 20 years, when you bring those costs all back into present value, it is not 1,800 times 20. 1,800 times 20 is 36,000, and what we've calculated with our discounting formula is 27,000, 27,100 almost. So, and that's because we discounted that value. It is not right to just multiply $1,800 by 20 years. Okay, that's where the discounting comes in. Time value of money. Let's move on to the next 3 costs. Wood chip replacement, labor for that wood chip replacement, and replacing the control structures. Those all occur in year 10. So those are single sums that happen in the 10th year of my planning horizon, which is 20 years. In other words, they're not series. So let's write single sum, and then let's do the formula here. So our single sum formula is there in the table at the top. I have my value times, start my parentheses, 1, that's the numerator, divided by, do a couple parentheses here, 1 plus I, that's my discount factor, in parentheses for that inside part, raised to the time that this cost occurs. So that's not my planning horizon in this case. In this case, the N is when that cost occurs. And then I in my parentheses for the denominator, and in my parentheses for that whole bracketed part of the formula. Okay, so I get $2,800.24. That's less than the $37.50 that the wood chip replacement cost me initially, but that's because we've brought that cost from year 10 back to present value. So I'm just gonna lock these parts of the formula in, lock that discount in by pressing F4. So you see H2 has two number signs by it that locks that cell in. And then I'm going to drag this formula down. Let me check the bottom one. So I'm bringing this cost, $2,500, that happened in year 10, back to present value using that discount formula. So that's right. Okay. So now we can do our sum total present value cost. This is easy. Equals the sum of all of these costs. That's my summation of my total present values for each itemized cost. Now let's do the equal annualized cost part. This is dollars per year over the planning horizon, and this is where the capital recovery factor comes in. So here I'm going to follow this part of the formula inside the brackets. That's my capital recovery factor. Equals, I'm going to start with a couple extra parentheses here. So my numerator equals I, discount factor, times 1 plus I want to add an extra parenthesis right here, raised to the N, that's my planning horizon. Okay, so I times 1 plus I raised to the N, and that's my whole numerator. Okay, divided by parentheses from my denominator. 1 plus I, close parentheses, raise that to the N, close parentheses for that part, minus 1, close parentheses for my denominator. Okay, and I have an extra set of parentheses in there, but that's okay. So my capital recovery factor is 0.664. And then to calculate my equal annualized cost, you see A in this formula. A is the equal value annual or periodic payment. In this case, it's just my equal annualized cost. So I'm going to do my value times my capital recovery factor. And that's that equation that's written in blue right there. So my equal annualized cost is about $3,000. And that's the dollars per year over that 20-year, the dollars per year that this practice costs me over that 20-year planning horizon. Now, if I wanted to calculate a cost efficiency, I would estimate in some way how much nitrogen the practice removed in kilograms of nitrogen removed over that lifetime. And then I would divide my equal annualized cost, dollars per year over the planning horizon, by my kilograms in removed, and that gives me a dollars per kilogram in removed per year, $1.20.